Hi guys, this is another short video to explain the solubility of an ionic crystals. Alright, it involves some calculations. So, how to determine that an ionic solid is able to dissolve in water, whether it's partially dissolved or fully dissolved or it's actually insoluble in water. Now we know that ionic crystals or ionic compounds, they are generally soluble in water because ionic compounds are charges. They have positive and negative charge, and water itself, H2O, will have polars, dipole, delta positive, delta negative. So both are actually polar. Usually they are miscible. They are soluble in each other, right? But for certain crystals or certain ionic compound, they actually appear as a precipitate. Let's say, for example, silver chloride. It is a precipitate. When you mix a silver ion solutions with a chloride ion solutions from two separate beaker into one, you can see white precipitate form. So what does it tell you about the solubility of silver chloride? It is insoluble in water, or maybe we can say it is just partially soluble in water. Most of them still maintain as a solid. All right. Now, how can we determine the solubility of an ionic compound? Based on this, we have learned these definitions before. We call that as enthalpy change of solution. Okay. Now, what is that enthalpy change of solutions? One mole of substances, referring to ionic compounds, dissolve in large amount of solvent, referring to water, under standard conditions. Okay, enthalpy change of solutions can have a positive values or a negative values. Now, positive means endo. It also indicates that if you have a positive enthalpy change of solution, it indicates the solid is insoluble in water when it is positive, whereas when you have negative value, it is soluble in water. Now, why is it so? Now, make it simple. When you dissolve a solid into water, let's say I have a solid crystals, I have 2 grams of a solid crystals, and then I have a beaker of water. All right, then you just dump this 2 grams into the water and you expect it to dissolve. Now, let's say the enthalpy change of solution, which measure the solubility, is an endothermic reaction, is a positive values. So if you just dump the solid into the water without providing any heat energy, do you think these endothermic reactions will occur? Definitely not, right? Because it's an endothermic reaction, meaning that you have to provide energy for this reaction to take place. So without heat energy, the solid will remain undissolved. Alright, so positive or endothermic enthalpy change of solutions mean the solid is insoluble. Whereas for negative is an exothermic reactions. Basically, an exothermic reactions, you don't need to provide extra heat. The reaction can take place by itself because at the end of the day, at the end of the reaction, it just releases heat to the surrounding. That's it. You don't need to input heat energy. Alright, so that's enthalpy change of solutions. Now, if I draw it out in a cycle, when you want to dissolve an ionic crystal, let's say, for example, I have the same crystal, sodium chloride, solid. All right. If you dissolve it in water, you will get sodium aqueous and chloride aqueous. Make sense? So this is enthalpy change of solution. So this equation indicates enthalpy change of solution. One more substance dissolved in water. Again, guys, because this is in a solid, in order for it to change in the gaseous, in order for it to change in the aqueous ions, you need to change them through stages. So what are the things happening here? First, you need to change the solid into gaseous ions. So basically, we are trying to break down the ionic lattice structure. So what energy involved here? We learn it from the Born-Haber cycle. If you try to break a solid or if you try to form a solid, the energy called lattice energy. So in this case, you're breaking a solid. We call that as lattice breaking, or you may just simply put it as lattice energy. All right. So once you've broken down the whole solid lattice, now they are in a gaseous ion form. This gaseous ionic form will start interacting with water. All right, so now you put in water, now you put in water. So the water now will interact or form bonds with the sodium gas ions, try to grab them. Okay, of course, the sodium positive ion is being attracted to the delta negative oxygen from the water, and the negatively charged chloride ion is being attracted to the delta positive hydrogen from the water. So once they manage to form a bond between them, they start forming bond with the water molecules, then the state will change from gaseous into aqueous. And what is the energy involved here? When the ions actually form bonds with the water molecules, we call that as enthalpy change of hydration. Or in short, we call that as hydration energy. Again, we learn about the definitions. 1 mole of gaseous ion dissolve in large amount of water. All right, we call that as hydrations. So in this case, we can see from this cycle, okay, from this cycle, we can see in order to determine the solubility of an ionic compound, we need to look at enthalpy change of solutions. But how can we calculate enthalpy change of solution? We need to look at the lattice energy and the hydration energy for both negative and positive ions. All right, now based on this cycle, they have derived an equations, a mathematical equations. So you can straightaway calculate whether a solid is soluble or not, given that the enthalpy change of lattice and hydration energy is given. So enthalpy change of solution is equals to, okay, hydration energy. Now in this case, the hydration here is referring to the total hydrations for both positive and negative ions. Means for hydration, you're supposed to have 2 separate values. One is for positive ions to react with water. Another one is for a negative ion to react with water. So you have 2 values here. You add them up, you get a total hydration energy. And this total hydration energy is going to minus the lattice energy. Okay, now in this case, because it's a mathematical formula, always bear in mind lattice energy can be positive or negative, right? In this formula itself, the lattice energy here that you substitute in here, it's always a negative values. Okay, so that the minus here with the negative sign, minus, minus, you get a plus. So you plus the lattice energy. And why is it so? Because in Born-Haber cycle, lattice energy is always negative because they are forming a solid, right? If you refer back to Born-Haber cycle, at the end, the last stage is actually form 1 mole of solid, so which is always negative, exothermic. But in this case, look at the arrow. I'm changing the solid into gaseous ions. I'm breaking down the solid. So the lattice energy is supposed to be a positive value. Makes sense? But the formula here giving you minus. So here you should put in the original negative lattice, and minus minus, automatically you are getting a positive values. Or if you don't like it, you can actually change the lattice energy on your own. The lattice energy involved here, you just change it into positive, which indicates lattice breaking, and then you sub into the value and you plus them up. That's it. All right, so this is the formula given. The only thing you need to bear in mind is the lattice energy that we sub in here has to be a negative value, so that negative, negative, you get a positive. You add them up. All right, then you will get enthalpy change of solutions. And the final answer is positive, meaning that it is insoluble. If it is negative, that means it is soluble. All right, let's do this. Now, draw 2 energy cycles to determine the enthalpy change of solutions of lithium chloride and sodium chloride, given the lattice energy for lithium chloride is -848 and that of sodium chloride is -776. All right, the enthalpy change of hydration for lithium, sodium, and chlorides are all given here. All right, so all the informations are given here. So you just need to draw the cycle out, or you may just use the equation, the formula, the mathematical formula to calculate the final answer. Let's draw the cycle out, right? So lithium chloride is actually changing from LiCl solid. First, they change into Li aqueous, Li plus aqueous plus Cl minus aqueous. All right, and then they break it down into lithium gas ions plus Cl gas ions, and then from here they separately react with water. then you get aqueous ions. All right, so now we try to put in the value. So enthalpy change of solution, of course, is unknown because we are going to calculate that. All right, and for lithium, what do we have here? Lattice energy is negative 848. Again, guys, see that? Negative 848. So we just put in negative 848, but later we know that this is going to change into positive values. All right, so lithium reacts with water, the hydration of lithium and chloride. So lithium is negative 499, and for chloride is negative 381. Now guys, bear in mind, this is one lithium and one chloride. Therefore, the answer, the value is 499 and 381. What if I have 2 lithium? Make sure you multiply by 2. Okay, but this doesn't apply for any group 1 metal because it's always 1. Anyway, so you got the value here. And how to get the enthalpy change of solution? Either you solve it using Hess law, or you just use the equations. All right, enthalpy change of solutions equals to what? All the hydration energy, 499, plus with negative 381. All right, that's the total hydration, minus, still remember, I have to put in negative values so that it becomes plus 848. Negative, negative, positive. And then you will get your answer. Let me do a quick calculation here. Negative 880 plus 848. Nice. So it's negative 32. So the enthalpy change of solution for lithium chloride is a negative value. Don't forget about the unit, kilojoules per mole. Yeah. So lithium chloride, is it a soluble or insoluble salt? Because it's negative, it is a soluble salt. All right, so this is a cycle, this is the calculations. Now if the question asking for like calculate the enthalpy change of solution, you may just show the formula and do the calculation without the cycle. But in this case itself, they say draw the energy cycle. Please make sure you show the cycle as well, and then you apply the formula, you get the final answer. Okay, so this is one of the examples shown. You can do it yourself for sodium chloride, exactly the same way. And then for part B, how would you expect the temperature to change when lithium chloride dissolves in water? We can answer it together here. Since the enthalpy change of solution for lithium chloride is negative 32, okay, when you dissolve in water. So what do you think about the temperature change? Exothermic temperature increase. Okay, temperature increases. When you dissolve lithium chloride, temperature increases. Why? Because enthalpy change of solution for lithium chloride is an exothermic value, is an exothermic reactions. All right, and that's it for this. And again, when you draw the cycle, please remember to balance it. In this case, it's just straightforward 1-to-1. What if it is magnesium chloride? See that? So when you balance the equation, you get magnesium 2 plus aqueous plus 2Cl minus aqueous. See the 2 here? All right. So later, when you do the hydration from Cl minus gas into Cl aqueous, the value, the hydration value for chloride, you need to multiply by 2. You get that? All right. So this is very important. Otherwise, you get a wrong value. Okay, that's it. This is a short video to show you how to do what is solubility of ionic crystals and how to do the calculations. All right, thank you.